After having this insight on the into the Hall coefficient, let's move on to the AC electrical conductivity of a metal. When we are talking about AC electrical conductivity, that means alternating current, we are going to apply a time dependent electric field on the metal. So, to calculate the current induced in a metal by time dependent electric field, we need to assume a form of the electric field. So, the electric field is assumed to have this kind of a form. It's in complex form, electric field is E omega e power minus I omega t, and we take the real part of this quantity, that is our electric field. Now, the equation of motion of the electrons for the momentum per electron, that is dp dt equals the damping term minus p over tau minus E times the electric field. Now, we want a steady state solution for this problem. So, let us consider a trial solution for this differential equation. For this differential equation, we can consider an exponential trial solution, Pt equals P omega e power I omega t, and we have to take the real part of this quantity because the momentum is real, and substituting this complex P, not the real part, this entire complex quantity, and the complex E, that is this entire quantity, not just the real part, into the differential equation, we can obtain something useful and then take the real part to get the physical quantity. That is a standard approach that you have seen elsewhere, maybe including other properties of electromagnetic waves. So, if we do that, we would find that we must satisfy a condition minus I omega p omega, this equals minus p omega over tau minus E function of omega. This you will find by putting this expression of P, complex expression of the momentum and complex expression for the electric field, into this differential equation here. Okay. Now, our volume current density J, this quantity is given as minus N E P over M. This is the current density. And in complex term, it can be written as, in complex form, it would be written as j omega e power minus I omega t, and we will take its real part for the real physical quantity. So, now putting this into appropriate place from this equation here, we can write j omega equals minus NE P omega over m, which is taking the value of p omega from this expression here. We can write this equals n e squared over m times e omega over 1 over tau minus I omega. This comes from here. Okay. Once we have obtained this, then it's the j omega, the current density, can be written as customary form of the Ohm's law, sigma omega, the conductivity as a function of omega, times the electric field, which is also a function of omega now. Here this quantity sigma omega is called the frequency dependent conductivity or the AC conductivity. And what is its value? Sigma omega can be written as sigma naught over 1 minus I omega tau, and sigma naught, as we have defined earlier, is nothing but n e squared tau over m. Now if we consider zero frequency, then sigma omega becomes sigma naught. Omega goes to 0 here, and if omega goes to 0, it's sigma naught over 1, which is sigma naught. So it correctly reduces to the Drude result for zero frequency. The most important application of this result is the propagation of electromagnetic radiation in a metal. So how does an electromagnetic radiation propagate in a metal? Maybe you have already learned that electromagnetic radiation does not propagate in an ideal conductor. There is no electric field inside an ideal conductor, and if there is no electric field inside an ideal conductor, there is no question of propagation of the electromagnetic wave. That's perfect, but there is nothing called an ideal conductor. Every conductor that we are surrounded with are real conductors, and at very high frequency, you can't expect that the electric field would instantaneously be nullified by the conductor. At low, if the electric field is of very low frequency, then that is valid, no problem with that. But if you have very high frequency, then it doesn't work. So how does the electric field get nullified? There are charges, free charges in the conductor, in the metal, that moves from one place to another to nullify this electric field, and that movement of charges, that requires certain time. That depends on the properties of the material, and if enough time is not given for those electrons to move around, then the electric field won't get completely nullified, and electromagnetic wave to some extent can propagate inside a metal, provided the electromagnetic wave is of very high frequency. Let's understand that mathematically. So if we consider current density J as a function of position and frequency, then it can be written as sigma omega, the conductivity, times the electric field as a function of position and the frequency. This is valid whenever the wavelength of the electric field, that is lambda, that is large compared to the electronic mean free path, that is L. So, that means this is valid when lambda, that is the wavelength of the electric field, when this is greater than L, which is the mean free path of the electrons. Now, this condition normally is normally satisfied in case of ordinary metals and visible lights. Now, if we assume that the wavelength is large compared to the mean free path, we may proceed like, in the presence of specified current density, that is J, we can write the Maxwell's equation if the J is given. The Maxwell's equations would take the form in CGS units, of course, because we have been working with CGS units. The divergence of electric field inside a metal, that is the charge free region, is going to be 0. The divergence of the magnetic field H here, that is anyway 0. The curl of an electric field is given as -1 over C del H del T in CGS unit, and the curl of the magnetic field H is given as 4 pi over C times the current density J plus 1 over C del E del T, which is the Ampere's law modified by Maxwell and expressed in CGS units. If we have these Maxwell's equations and if we look for a time dependence of the form of e power minus I omega t, then in case of metals we can express the current density J in terms of the electric field E using the curl of E, that is minus del square of E, and this would be given as I omega over C curl of H. This quantity equals to I omega over C 4 pi sigma over C times the electric field minus I omega over C times the electric field. This implies that minus del square of the electric field is given as omega squared over C squared 1 plus 4 pi I sigma over omega times the electric field. This has the form of the usual wave equation. The usual wave equation looks pretty similar to this. And if this is similar to the usual wave equation, let's write it in the compact form of the wave equation. Del minus del square E equals omega squared over C squared epsilon omega E, where epsilon omega is the complex dielectric constant. So this equation is just like the equation of electromagnetic wave in a dielectric material with this dielectric constant here. And what is the value of this dielectric constant now? The complex dielectric constant, this equals 1 plus 4 pi I sigma over omega. But this expression, whatever we have obtained, this is not for a dielectric material, this is for a metal. Now let's consider different ranges of frequency. If we are at a frequency that is high enough to satisfy this condition, omega times tau is much greater than 1, if this condition is satisfied, then to a first approximation we can write the dielectric constant equals 1 minus omega p squared over omega squared. So we have introduced a new quantity omega p here. Omega p is known as the plasma frequency. This quantity is given as omega p squared equals, as you can see from earlier, 4 pi Ne squared over m. Now, when epsilon, that is the dielectric constant, is real and negative, that means when omega is less than omega p, in this kind of a situation, the solution would be an exponential decay in space. There would not be any propagation. That means if this electromagnetic wave enters a metal, its intensity will decay very rapidly as it gets inside the metal, as it progresses through the metal, but that electromagnetic wave won't propagate into the metal. So there would be a skin region of that metal in which that electromagnetic wave will enter and sharply decay. The intensity will sharply decay for this kind of a situation. That is no propagation. When the dielectric constant epsilon is positive, that means omega is greater than omega p. In this situation, the solution will become oscillatory and the electromagnetic wave can propagate inside the metal. In this condition, the metal becomes transparent. EM wave propagates transparent metal. This is something interesting. Metals should not in general be transparent. Metals usually reflect electromagnetic wave, but when this condition is attained, that is the frequency of the incident wave is pretty high, higher than the characteristic plasma frequency for that metal, that electromagnetic wave propagates. That means the electrons cannot move so fast that it can nullify the electric field inside the metal. Now, if we express tau, that is the relaxation time, in terms of resistivity, then we can write omega p times tau, that equals 1.6 into 10 power 2 Rs over A naught power 3 by 2 1 over rho mu. The alkali, in case of the alkali metals, it has been observed that for ultraviolet rays, the alkali metals become transparent. So, the plasma frequency, the omega was the angular frequency, nu is the actual frequency, that is omega p over twice pi, this quantity equals 11.4 times Rs over A naught power minus 3 over 2 into 10 power 15 hertz, or the wavelength lambda p, the plasma wavelength, that is C over nu. This can be given as 0.26 Rs over A naught power 3 over 2 times 10 power 3 angstrom. So, this is valid for the alkali metals. That is what we find. This should be minus. Okay. So, this is a very important consequence, that at very high frequency the metal becomes transparent. Let us consider another important consequence, the second important consequence. The electric charge density has an oscillatory time dependence. So, the electric charge density is, it goes as e power I minus I omega t. If we write down the equation of continuity that we have learned in electromagnetism, then we can see that the divergence of the current density is minus del rho del t, which is nothing but the conservation of charge. So, rho is the volume charge density in this context, and this means the divergence of j omega, this is I omega rho omega. And now if we consider the Gauss law, we can write the divergence of the electric field, that equals 4 pi times the charge density. Now, with this, comparing these two equations, we find that I omega rho omega equals 4 pi sigma as a function of omega, rho a function of omega, and this equation will have a solution provided we have 1 plus 4 pi I sigma over omega. This quantity goes to 0. Only then this equation will have a solution, and this is the same as the condition for propagation. Now, what does this mean? This means a charge density wave is created for the propagation of the electromagnetic wave. So, there is a charge density of the electrons in the system, and that charge density itself oscillates when the electromagnetic wave propagates through the metal. And this kind of oscillation is called the plasma oscillation. So, we can see a wave in the charge density itself as a function of as a consequence of the electromagnetic wave passing through the metal, and this happens only when the frequency of the incoming electromagnetic wave is pretty high. Otherwise, that electromagnetic wave gets reflected only it can only penetrate the skin of the metal, nothing beyond that. But with a very high frequency, it can go through the metal, pass through the metal, and it creates an oscillation in the charge that is there in the metal.